Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, to our next lesson. This lesson is going to integrate what we've been learning about adding fractions together and what we know about probability. And we're going to learn a new concept having to do with probability, which is called compound probability. Now, what we were doing earlier in this chapter where, what's the probability of flipping a head, what's the probability of rolling a die and getting a 2 on the die, that was considered simple probability. Simple theoretical probability. But as I'm sure you're aware, things can get more complicated, a little bit more complex. So we have compound probability. And to define compound probability, there you go. Compound probability is probability based on compound events, more than one event, where either one event or another event could occur. So if you consider rolling the die, this is a 6-sided die. You roll it, you can get anything from 1 to 6, and you've got a 1/6 probability of getting any one of those particular numbers. Now, of course, remember experimental probability. I could roll this 10 times and get a 4 every single time. It could happen. It's not likely that it would happen. It's very unlikely, as a matter of fact, but it could happen. So we're going to deal with the theoretical probability for figuring out our compound probabilities for this particular chapter unit. So basically what we're talking about with compound probabilities for this example would be like, all right, if we all agree that the probability of rolling a 1 with a die, a standard number cube, is 1 out of 6, since there are 6 sides and only one of them have the number 1, okay, that's great. And we agree that the probability of rolling a 3, since there's only 1 3 on the 6 sides, would also be 1/6. So what's the probability of me flipping this coin and getting either a 1 or a 3? Okay, so if you think of the 1 as being a winner, you got a 1 in 6 chance of winning. If you think of the 3 as being the winner, you got a 1 in 6 chance of winning. But if you win with either a 1 or a 3, what do you suppose is going to be the process that we're going to use to figure out that probability? That's what this chapter lesson is about. Okay, so far in this section, you have worked with probabilities involving one specific desired outcome. Now you will investigate probabilities of compound events. Compound events are events with combinations of outcomes. In today's lesson, you will find the probability that either one event or the other event occurs. And in chapter 4, we're gonna focus on the probability of both one event and another one occurring. So you could have like an either or situation or a both of these things happen kind of a situation, which is also compound probability, but involves some different mathematics. Okay, so think about these questions as we work today. How is the probability related to the probability of a single event? Either what event or what other event are we interested in, and does our answer make sense? Okay, so let's start off. I'm going to have you pause the video and please recreate this. This is like a spinner, okay? And it's got different sections. I'll read this out. Just listen to what I'm saying here, and then I want you to pause the video, and I want you to draw this out. Okay, so Thomas helps around the house by doing one chore after school. Each day, Thomas and his aunt use the spinner at the right to decide which chore he will do. Here's what Thomas knows. The sections of the spinner for rake leaves, this one right here, and do laundry are the same size. Okay, so that's important. Those are equal to each other. Also, the section for clean bathroom, this section here, and vacuum, this section here, are equal in size, and they make up half the spinner. So I just decided to make a list over here. Based on what I know from this, from how these are labeled, I know that the vacuum is 1/4 of the circle, 1/4 of the spinner, which means there's a 1/4 probability that if you spun the spinner, it would land in this section. And since clean bathroom is equal to that, then I just went ahead and wrote 1/4 for the clean bathroom as well. Then on to the raking of the, well, first of all, we know the clean bedroom, that's given, so it's 1/3. We don't know what these two are, but we know they're the same. Okay, so what strategies can we use here to figure out the answer to our questions? Let's ask the questions first. If you haven't already done so, you should have paused this video and drawn a picture of this and label it properly. And you don't necessarily have to write these probabilities on the side. You could just write them in. Like, you know, I could have just done this, I suppose. Instead, this is also a 1/4. And then we have to figure out what those two are. So what is the probability that Thomas will spin laundry? All right. What do you think? Spin laundry is, or not spin laundry, do laundry. That's just this section right here. It seems to me we've got to figure out what this section is right there, right? And then take half of it, because each one they're equal. Oops, let me get that bigger. So what do we do? Well, if you'd like to pause and see if you can figure out the answer on your own, and then unpause and watch me walk through the process to see if we got the same answer, that would be awesome. Otherwise, just follow along with me and take good notes, okay? So this is what we know here. We know that we're going to add in, oh goodness, sorry, let me extend this a little bit. Okay, so we won't have to deal with that. Okay, so we know that we know all these probabilities here, but these two are mysteries. So I just put the variable p in there for the probability of each one. And since we know they're the same, we're going to use the same variable, right? That's kind of a rule of algebra. If you have these are different, we'd want to choose two different variables, but they're the same, so they can be the same variable. So I think where we start is let's add together the 1/4 and the 1/4 we know makes up 1/2 of the spinner, right? 1/4 plus 1/4 is 2/4, and 2/4 is the same as 1/2. Then we have to add these sections together. So we know what is the total sum of these three sections. Once we know what that total sum is, we can use a little bit of logic to figure out what the rest of it is. So let's add them together. Let's figure out what is 1/3 plus 1/2. Remember, using the coat of arms, you can multiply 3 times 1 is 3, and 3 times 2 is 6. 2 times 1 is 3, or 2 times 1 is 2, and 2 times 3 is 6. 1/2 is the same as 3/6. 1/3 is the same as 2/6. They have common denominators, so we can now add those together. And I combined like terms here, so you've got two p's there. So we know that this section here represents 5/6 of this circle. So what would the rest of it have to be? Doesn't that mean that the rest of it, if we took away the 5/6 from the total, that you would get 1/6 is the remaining? So that means if we go all the way back up in here, this is 1/6 of the total. So what's half of 1/6? 1/3? No, that doesn't work. Half of 6 is 3, but this isn't going to be, one of these isn't going to be 1/3. This was 1/3. So how do we find half of 1/6? Well, half of 1/6 is going to be what you do when you take 1/6 and you multiply it, that's supposed to be a 6 there, times 1/2, right? And so that's how we're going to get 1/12. So if you said do laundry was 1/12 probability, you were correct. That is exactly right. So I'll go ahead and write this in. We'll call this 1/12, and then since this is equal, then this will also be 1/12. That's a terrible 2. Okay. So Thomas hates to clean the bathroom. When he spins a spinner, what is the probability that it will not be a clean bathroom? And then explain how you found the answer. Okay, so basically, he hates cleaning the bathroom, which means he does not want this section. He would be okay with all the rest of them. So if this is 1/4, what does the rest of it all combined have to be? Thinking, what would it be? It is 3/4, right? So if the probability of cleaning the bathroom is 1/4, then the probability of not cleaning the bathroom would be, in this case, 1 minus 1/4, which would be 3/4. Okay? All right, moving on. Okay, Thomas's aunt hopes that he will either spin clean bedroom or rake leaves today. So what I did is I took this spinner and I shaded in the portion that his aunt would be happy with. Now, notice that we're using the word or here. You're either doing this or that, which makes essentially both of them winners, okay? So she would be happy with cleaning the bedroom, which is a 1/3 probability, and she would be happy with raking leaves, which is the 1/12. So what do we do with those two fractions to figure out what is the new probability of this bigger red section? Well, so let's get to the first part first. We know that the clean bedroom is 1/3 and the rake leaves is 1/2. So what are we going to do here? What are your thoughts? Well, you've got to add them together. That's the process. When you're working with the word or, oops, stop it. That's not what I wanted to do. There we go. When you're working with the word or, that implies that you are going to add those two together, because what it does is it takes this probability, the 1/3 and the 1/12, and you combine them to make a bigger winning section. And so that means you're going to add the two together. So with that in mind, what is the probability of him either getting rake leaves or clean bedroom? That would be 5/12 probability. Okay, so let's get this in your notes. When finding the probability of choosing either one or another item, the word or is critical here, you will add the probabilities together. That written in nice and neatly. That will be very handy for you later on in the year when you need to go back and look through your notes. You've got a probability problem that involves the word or. If you don't remember it, you can just look at this. All right. Ms. Wynn lets her students borrow pens and pencils on days when they have a quiz. She has a paper bag containing hundreds of wooden pencils, mechanical pencils, and blue pens. Stuart forgot his pencil, and it is a quiz day. So Miss Wynn tells him that 1 out of every 3 students who reaches into the bag pulls out a wooden pencil. 2 out of every 5 students pull out a mechanical pencil, and the rest pull out a blue pen. What I'd like for you to do is I would like for you to record all of this right here. This is important information that we're going to need as we go through and we solve these problems. Okay, go ahead and pause the video and get that recorded. All right, so looking at question A. If Stuart reaches into the bag without looking, is it more likely that he will choose a wooden pencil or a mechanical pencil? And then it says to justify your thinking. Well, we do know those two probabilities, right? We know 1 out of 3 pull out the wooden pencil. So let's go ahead and jot that down. That's the probability for the wooden pencil. And then 2 out of 5 get the mechanical pencil. So we got to compare those, right? We can use our inequality symbols to compare those, but we can't really compare them until we have common denominators. So remember how we use the coat of arms to figure out what a common denominator would be? Let's do that here. Let's take 5 over 15, and 3 times 2 is 6. So 1/3 is equivalent to 5/15, and 2/5 is equivalent to 6/15. So that makes 1/3 less than 2/5, because 5/16 or 5/15 is less than 6/15. So our answer would be the mechanical pencil has the higher likelihood because 2/5 is more than 1/3. So how can you describe the probability that Stuart will pull out some kind of a pencil, whether it's a wooden pencil or a mechanical pencil? By using the probabilities that you already know, consider what you know about adding and subtracting fractions and see if you can, if you already have a strategy to write this probability as a single number. Well, I think you know what to do now, right? Because we're taking the 2 individual probabilities and we've learned that you have to add them together, correct? So the probability of getting either a wood pencil or a mechanical pencil would be the sum of those two probabilities. Now, I think you can see what the answer is going to be, but there's another stoplight problem that we can work through here first and just talk about this a little bit, because this is another common mistake that students make. This is actually the most common mistake that I've ever seen teaching all my years when I used to teach 5th graders all the way up through 8th graders. Felicia was trying to find the probability that she would pull either the wooden pencil or the mechanical pencil out of Miss Wynn's bag from problem 121. I think I need to combine the probability that I will get a wooden pencil with the probability that I will get a mechanical pencil. So she set up the problem this way and then drew these pictures. Now, she wondered, could the sum be 3/8? Is that how we do adding? When we add two fractions together, are you adding the numerators and the denominators together? And the answer to that is no. That is absolutely not what we do. You've got to get a common denominator. You've got to rewrite these fractions as equivalent fractions with the same denominator in order to add them, okay? Now, one little side note, 3/8 all on its own is actually less than either 1/3 or 2/5. But I think it's less than 1/3. Let me check. 3/8, 3 divided by 8 is, okay, so technically 3/8 is a little bit more than 1/3, but it's still less than 2/5 because 2/5 is the same as 40%. No, 2 divided by 5 is 0.4, right? So, and this was 0.375. There's no way you can add those two positive fractions together and get a sum that was less than one of them. So 3/8 doesn't even make sense as an answer, okay? So we already know what the answer is, right? Because we saw it on the previous page. We're going to get the common denominators, and we're going to add those fractions together. So that's the probability. Going back to this problem, the probability of pulling out either a wooden or mechanical pencil would be 11/15, which kind of interesting now. They didn't ask us this question, but now you know the probability of pulling out a blue pen. It's going to be 4/15, right? Since you're going to take all of them, and what do they all have to add up to? They all have to add up to 1. So we can use a little bit of algebraic reasoning and logic to figure out the probability of the blue pen. All right, how many people play cards? I grew up in a family where we played cards together all the time. Now, we lived in Michigan, and all winter long, there's nothing to do but sit inside your house, so we had a lot of time to play cards. If you don't play cards very often, we're going to review the standard deck on the next page. So Steve shuffles a standard deck of 52 playing cards and starts to turn them over one at a time. So what is a standard deck of 52 cards? Please, you don't have to worry about copying all of this down. You can just look at it, and you can reference this information. It's on the internet. I took an image from the internet and pasted it here. Notice that there are 4 suits. You got clubs, spades, hearts, and diamonds. The clubs are the black cards, along with the spades, and the hearts are red along with the diamonds. Okay. Notice that there are 13 cards in each suit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, with 3 cards in each suit being the face cards. And typically, the cards go in order from least to greatest, where the king has the highest value. But there are different games where, like the jack, if you play a game called euchre, jack is more powerful than the king. And oftentimes you'll have the ace is actually the high card, the best card, instead of the lowest card. It just depends on what games you're playing. But at any rate, these are a standard deck of cards, okay? So if they have 52 cards in them, and you pull out 3 cards, you pull out an ace, a 4, and a jack. You've taken those cards out, you're not putting them back into the deck. How many cards are left in the deck? So you had started with 52, you took away 3, how many remain? That would be 49 cards that are left in the deck. So now when you're finding probabilities, you've taken 3 of the cards out. So your total is different. Like if we started, we would have said, what's the probability of pulling out an ace? You would have said, well, there are 4 aces and there are 52 cards, right? But now that we've changed the total, Now we're getting a new total on the bottom. So how many remaining cards are there in the deck? There are now, how many remaining cards are aces? You took out one ace, correct? So how many aces remain? That would be 3 aces left. And now what's the probability of the fourth card being an ace? Well, doesn't that mean now for your next draw, you've only got 3 to choose from, and there are only 49 cards in the deck? Oh, hold on for a second. Much better. Okay, so yeah, you took out one ace, but left 3 aces in there, so now your probability is going to be 3 out of 49. So that would be the probability of the fourth card being an ace. However, the fourth card was not an ace, it was a 2. And then the fifth card was a 5. So how many total cards have been removed from the deck? A total of 5 of them, right? The fifth card was taken out. So our 52 minus 5 means we now have 47 cards. And now what's the probability that we're going to get a king? How many kings are in the deck? 4. Have any of them been taken out yet? Ace, 4, jack, 2, and 5. Nope, all the kings are still in there, which means you got 4 out of 47 is now your probability of getting a king on the 6th card that you plan on drawing. It is this type of probability, understanding the deck, that is the difference between an amateur card player and a really good professional card player. Professional card players know the probabilities. They know which cards they've seen out. They know how many are left. They know what the probabilities are, whether it's highly likely or impossible or certain. You probably know certainties in poker, but they can bet accordingly. So understanding how probability works can help you a lot when you're playing card games. It goes back to the winning strategy. Cards are fair because everyone's got an equally likely chance of getting any of the cards in the deck. But if you understand how probability works, then you can have an advantage over other players. All right, so that ends our lesson. I'm pretty sure that's it. Yep, that is all. So thank you and good luck on the homework. And we've only got one more lesson before we're going to be taking the chapter test. So good work so far this chapter, and we move forward. Bye.
Hey, feeling good, like I should. When in dark, walk